long. In many ways, it's my fault because of the time I took for lecturing. There's also the fact that you're doing your first attempt at this whole hypothesis and then the test. And so let me do a quick, not necessarily what it should have been for this one, but in general, how you're doing the hypothesis and test and so on. So you have to have first, actually I'm going to start by writing, I meant to put this as a change in the instructions for the lab write-up. My observation. And so for yesterday's lab, the observation was simply a dropped ball falls down. And then we have the hypothesis. And I'm going to go with a really crazy hypothesis. Right? One that I know is wrong. I'm going to say the metal is attracted, that's supposed to be the word attracted. So the earth must be, let's say the floor, must be magnetized. Pulling the ball down. Now, even though I know that's false, that would have been a fair hypothesis, right? That could have been the reason. You know, if we were somewhere where we were in a microgravity situation and we magnetized the floor and we had this, it would have made it fall. So that's a fair hypothesis, even though I know it's not the correct one. Now, I wanted you to do your best in terms of try to think it through and not just make something up, but still, that would be a fair one. And then I need to have my test. And so first I say, so the test I gave you was specified. You're going to drop it from 1 meter and 2 meters and compare the time to fall. My hypothesis predicts that the acceleration is greater, closer to the magnetized floor so dropping farther away will lower the acceleration. Initial acceleration. Now, I'm not even worried right now if I have done my calculations for acceleration and time correctly, because you're not expected to have knowledge about how acceleration works. And so I'm just doing this off the top of my head without really thinking about it. So since it's going to have lower initial acceleration, it's going to take more than than 2 times as long to fall. Like I said, I haven't done any calculation here. I could be wrong in that prediction, but that's what I'm thinking my prediction is from my hypothesis. And so then I do my test. If it takes more than 2 times as long to fall 2 meters, then I have confirmed my hypothesis. If it takes exactly twice as long, it failed. If it takes less than twice as long, it failed. And so that's the kind of thing that you're supposed to have for that hypothesis and test part. We're going to be doing that most labs, and the reason is to get a better feel for how scientists are developing their experiments and what they're trying to do with their experiments. Because scientists don't just have a prescribed, now do this. By the way, somebody in the back corner there left this lab book. Chad had a question.
Yeah, I was just going to say, unless I missed it, I don't think observation was in the lab guide.
That's right. It says your hypothesis. You have to have your hypothesis based on a observation you make in your daily life. But I meant to actually pull it out and make it a separate thing, just so it would be clear that you really do need to start with an observation. You don't just start with a hypothesis about something you've never seen.
So for future reference, we should put an observation in there.
Well, I'm not going to mark you down if you don't put it separate, because it doesn't say to put it separate. You still have to have the observation. It says to put it. It just has it in the hypothesis, and I put it separate. Right, so if you don't have an observation, yes, I will mark you off. But you don't have to say observation colon. Okay, so do people understand that hypothesis and test thing, the goals and how to do it? Because clearly if people don't understand, then it's going to be a lot harder and a lot more time consuming. Cassie?
Yeah, how there are like 6 questions, is that incorporated into any of these, what you're looking for, like tests or equations underneath those headings, or is this completely separate? Like,
You're talking about all the questions that say like Q/C.
Yeah.
The Q/C stands for question/comment. I'm looking for you to talk about something there. And those are things that you should have in your data calculation and discussion section.
oh,
So as you get to things, you should be writing down, like, okay, so we did our experiment, it worked perfectly. You should write that down. You got the question that comes right after, says do the experiment, answer the question right there. So you should just have a timeline that you can follow as you look through your report of when things occurred.
so kind of like follow like test, equations, apparatus, experiment, and then the next section where it's some data calculation discussion would be those 6 questions or other questions in there?
Well, interspersed with the data. Right, I mean, like the first 2 questions were supposed to be before you did, or the first 1 question was before you did anything.
Yeah.
Right, before you dropped a ball or anything, you were supposed to speculate on how long you expect it would take for it to drop a meter. So you write that in first, and then after you've written it down, then you do a few drops and say, I think I might have been a little off. Or you might say, that seemed right on. And then you estimate how much air you think you could have. And then you go on to do your measurements and so on. And so you just have those things written down in the order.
Okay, I don't have to put QCs.
It'll make it a lot easier for the grader
Yeah.
if you set them off with that. And the grader right now is me. If you set them off with that, so I can see, yes, here's where she answered, QC number 1. Right, I put them in there for you like that, so you would clearly identify where I'm expecting specific answers as well. Chad?
So then to clarify then, so we'd have the experiment explanation, and just go through the whole experiment explanation separately, and then after that we'd have a QC1 data, QC2
Yeah,
data.
and that experiment section shouldn't be huge, right? You're supposed to summarize, keep it short. I mean, I'm hoping for less than half a page. A quarter page would be ideal, although sometimes there's just too much to fit in a quarter page. But I don't want some long, detailed thing, just enough that somebody else could reproduce it.
So pretty much in summary, the observation is what we see. The hypothesis is why we think we see what we see, and the test is what we think will happen.
For the most part, yes. The observation, I seen this thing. That's using the grammar of one of my friends from college. I seen it. And then the hypothesis is a reason why you think it occurred that's based on scientific ideas that would explain why it happened.
Right.
And then the test has to take a prediction from that hypothesis and test to see if it does in a different situation what your hypothesis predicts. Your test obviously is not going to go back to the same thing of your observation, or else you're just repeating your observation and not testing anything new. A few other things about the lab. I was starting by saying, I'm sorry. I know there are a number of people who did not finish, and I tried to make sure people kept their balls so they can use the same ball when they come back to finish. It should not, if you have the hypothesis part done, it shouldn't take very long for the rest, because you're just dropping a ball 5 times and measuring the time it takes to fall, and then measuring its size. I'll be here this afternoon from 2:30 to 4:30, so that would be a great time if it's available for those who don't have it done yet. some things you might be curious about now that the experiment is for the most part over. How long did it take for the ball to drop 1 meter?
Yeah, about 0.4 seconds.
Okay, about 0.4 seconds. Okay. Got some numbers here. Now let's compare to what it really was. Now I say what it really was because the physics is pretty sound on this. It's been tested over and over and over and over. What we have is the distance that it fell is equal to 1/2 the acceleration of gravity multiplied by the time of fall squared. That's for if you drop it from rest. And so in our case, we want to solve this for time. Time is equal to multiply by 2 divided by g, 2d over g square rooted. So that's going to be the square root of 2 times 1 meter divided by, and g, which you don't know yet unless you've taken physics before, is 9.80 meters per second squared. And so if you do the square root of 2 divided by 9.8, okay, the way I have this set up, it's going to just look funny on the screen. You won't see me doing the math. It's actually really cool. Actually, I'm going to make it so you can see just so I can show off. That's not it. I think this, oh, come on. Sometimes it's just slow at responding. Hide the presentation. There we go. All this so I can show off the cool little calculator that I use. That was a big calculator. And so my number was square root of 2 over 9.8. And so that's how long it should have taken. 0.45 seconds. So now that you know what it actually should have been taking, you look at those numbers. Every one of the 3 people who were brave enough to share their results had a slower or a faster time than that. That indicates there is some very common error in the measurement. And so when you're thinking about the errors in the measurement, think about what would have made everybody measure the time as too short for this. And yeah, I won't tell you what I do to try to compensate for that because that then leads you to what it is, and I want you guys to spend some time thinking about it. Okay, the lab is due tomorrow night at 11:55, uploaded to Moodle as a PDF document. You just go in Moodle to Measurements Laboratory. There's a laboratory section in Chapter 1, Measurements, and you upload it there. If you have any questions, make sure you contact me so that we can make sure you know how to do it and get it done. Any questions on the lab before I go to the actual lecture? Any more questions? All right, then let's go to the top of this. Here's what we're going to be looking at today. We're going to be looking at some of the very beginning things in kinematics. So we have, over here is a nice graphic I found. Here's the guy who made it. He has his name up there as well. And it actually is pretty useful. We're going to be covering today just the stuff above that green line. But it's a really useful little cheat sheet for reminding you of the important things in kinematics. And so if I zoom in on this, let's see what information he gives us. So we have words here, scalar and vector. Scalar, spelled with 2 A's, is a word that means that we have a value that has a magnitude, how big it is. Magnitude means how big it is, its size, but doesn't have a direction to it. Does it have units? If it's a scalar, is it going to have units? Yes, because naked numbers are fairly useless most of the time. There are a few cases where you don't have units. But pretty much, the scalar is going to have units. But it does not have direction. Whereas the vector here has magnitude, how big the value is, and the direction. Now, in my class on Tuesday, I was talking about the unit vectors and which one our textbook uses. Maybe the reason our textbook didn't take off and was sold to the free people is because it doesn't use unit vectors. When we get to that point, I will choose one of the standard conventions and go with it, because I think unit vectors are kind of important for understanding vectors better. But I just wanted to clarify that since I talked about it for the 8 people in Physics 251 yesterday. Okay, we have distance and speed on the left side. Those are scalars. So distance doesn't have a direction, speed doesn't have a direction. That's what we can read from that. On the vector side, we have displacement and velocity and acceleration. So those things do have vectors. Now you can have acceleration over here as well. Let me just put ACC. You can have acceleration without direction. We still call it acceleration. And so there's no special word differentiating the vector form of acceleration from the scalar form of acceleration. And in fact, in most cases, that's true. There's no special word to tell you if it's a vector or not. The only one that really has a special word to tell you the difference is speed versus velocity. Distance and displacement are slightly different, as we'll see in just a few minutes. The units, very important. Units for distance and displacement are both meters. Units for speed are meters per second. It's the distance per unit time. And then the bottom one, acceleration, not a topic of the day, but acceleration has an odd set of units, meters per second squared. Nobody's watch will time in seconds squared, right? That sounds ridiculous. But in this case, it's saying the change in speed per time. So since speed is meters per second, and you're looking how much that changes per time, you have to divide by seconds again, and that's where you get the unit of meter per second squared. There's no such thing as a second squared, but the unit of second squared still makes sense. Over here, actually, this picture illustrates in a nice clean way the difference between the distance and the displacement. Now, distance is a scalar. There's no direction to it. Displacement is a vector. Vector means it has direction, and it points from the starting point to the ending point. So, for instance, if I start on this side of the desk and I walk over to this side of the desk, I had a distance of, let's say, 3 meters. I had a displacement of 3 meters that direction. So my distance and displacement have the same magnitude there. But I could have done something different. I could have done like that picture. I could have done a little ziggy-zaggy walk, and I get over here. The displacement was 3 meters again. But the distance was more because I walked in a circuitous route to get here. So the distance and displacement don't have necessarily the same magnitude for the same trick. In fact, the example I love to use is, let's say that I am jogging on a track, and I do 1 lap, because for me that's a victory. Okay, I have to tell you, I wasn't always this way. I had blood clots in my lungs 8 years ago. Time flies. And I've never had the stamina to run after that. Before that, I could... It makes me sad. Anyway, just have to point out, although I was obese, I could still exercise before then. I still go to the gym, exercise, just stamina is for crud. Back to the topic. So, I run 1 complete lap. My distance, assuming it's a 1/4 mile track, is 1/4 mile. What's my displacement if I ran a full lap? 0. Because the displacement is the straight line vector pointing from where I started to where I ended. And if I start and end the same place, my displacement's 0. Now when we get down to the next line, the velocity and speed, the velocity is based on the displacement. The speed is based on the distance. And I'm going to now leave this graphic, but I want to show you the cool things there and do some definitions. So position. Once again, using the vernacular of my good friend Larry, who we almost share the same middle name, but his is spelled L-E-A, so I just called him Larry Leah. Position is where you at. Your location, your position. And we're all pretty comfortable with that idea, right? My position is back here behind the podium. Your position is sitting at your desk. And in physics, we're going to define those locations with a reference system. We'll have a reference frame. For this classroom, I would use the classroom for my reference frame. I'd say, okay, I'm going to consider that corner of the room 0, 0, 0 in the x direction, 0 in the y direction. I have to find what x and y are. What are x and y? They're just labels for the directions. So I would just randomly say, okay, I'm going to call this the x direction. So x is 0 here and gets bigger as I go that direction. Y is 0 here and gets bigger as I go that direction. And so if I take Jaren's position, I'd say, okay, his x position is right about 2 meters. So he's 2 meters in the x direction, and his y position is about 3 3/4 meters. And so I have his position with both an x coordinate, how far he was that direction from my origin, and a y coordinate, how far it was that way from my origin. Of course, we live in three-dimensional space, don't we? So we also need one that's perpendicular to that vertical. And I'd say, well, his feet are on the floor, so I'll put in 0 for his vertical. With these dimensions, I need them to be perpendicular. I have my x direction perpendicular to my y direction. If they're not perpendicular, you don't have a unique description. The third dimension had to be perpendicular to both of the first two. So you have 3 mutually perpendicular directions when you're doing your coordinate system for 3-dimensional space. So your position is specifying in your space, and of course for our textbook problems, we'll start with a 1-dimensional space, forward and backward. But then we'll move forward to 2-dimensional space. We'll have forward and backward and up and down. We really won't do much in 3 dimensions because it's the same extrapolation, it's just getting harder. If you can do 2 dimensions, you can do 3 dimensions, it'll just be harder to do 3. So position is your location or the location of the object. Distance. Distance is the covered ground, like how much ground you covered in a set time. So, if I walk for 1 minute, the distance I walked might be, I don't know, let's just say 50 feet. I was moseying, really moseying to go only 50 feet in a minute. And if I walk for 2 minutes, I might cover another 50 feet and have a total distance of 100 feet. So the distance is the distance that I've covered in a certain amount of time. The displacement we've talked about a little more carefully. That's the vector going from starting position to ending position. Those are very simple, really. Speed and velocity aren't difficult, but we start to have more interesting things that can crop up. So speed, the average speed is equal to delta x over delta t. Now our textbook, instead of putting v with a subscript of avg, how does it indicate average? it puts a bar over it. So our textbook would have written this as V with a bar over it. So that's the average speed. It's the average speed over this time of delta t. That triangle is not pronounced triangle. It's pronounced delta. It's a capital D in Greek. And that delta means the change in. And the change in is always the final value minus the initial value. So delta x means your final x minus your initial x. Delta t means your final t minus your initial t. Now the textbook, like every physics textbook I've ever used, makes a simplifying assumption for time. And that is that we're going to always start at time equals 0. Since time is just basically when you start your stopwatch, we'll say we're going to start our stopwatch at time equals 0. That allows us to put zeros a lot of places in equations instead of having to do more calculation. So that's the average speed. This average speed over whatever time delta t is. As you shrink delta t smaller and smaller and smaller, you get closer and closer and closer to an instantaneous speed. An instantaneous speed would be how fast you are traveling at just one instant. Now, after I talk about velocity, I'll come back to that. Velocity here's the equation. Notice on top of the V, I now have an arrow. Not just a bar like average, but an arrow. The reason I always put a subscript AVG is because I have no way of differentiating, like V with an arrow, V with a bar. Did I just draw a sloppy arrow? It would be too confusing for me. So I put the AVG, so when I have that above, I know, hey, that's an arrow above. The arrow above means it has direction. If it has direction, what is it? It's a vector, so the vector form of speed is velocity. So V with an arrow above it is velocity. X with an arrow above it is going to be displacement. X without the arrow was distance. X with the arrow is displacement. One's a vector, one's a scalar. So this would be the average velocity, again, over the same delta t. Notice time is not a vector. We don't have a direction for time. Although, as the song says, time keeps on ticking into the future. Time only goes in one direction. We can't reverse time. But it doesn't actually have a direction. When I say it goes in one direction, I simply mean it only goes up. Unfortunately, my bank account can go both ways. Apparently, my stock portfolio can only go down. It's if you've been paying attention to the stock market. Yeah. But it'll come back up, right? Just don't sell until then. Don't. Now, if you shrink the time for the velocity, you'll get closer and closer to an instantaneous velocity. If you have an instantaneous, that is if the delta t is extremely small, the change in time that you're measuring is very small, there won't be any difference between the distance traveled and the displacement. Because in an incredibly small amount of time, no matter what path you're taking, it's going to look like a straight line if you choose a small enough time. So the instantaneous velocity has the instantaneous speed plus direction. So instantaneous velocity and instantaneous speed have the same magnitudes. It's just the velocity has the direction. Now, when you're driving your car, what does your speedometer tell you? Does it tell you the speed, the average speed, the velocity, or the average velocity? It tells you the instantaneous speed. Yeah, I should have said instantaneous instead of just speed. It tells you the instantaneous speed. So we're getting an instantaneous value. It's not perfectly instantaneous, but it's over very small time amounts, which is as close as we can get to the instantaneous value. Now, I actually have some clicker questions that I intended to do before I started lecturing, but guy gets carried away. So the first one is a true or false question. I have created my account on Expert TA and will have the first assignment completed tonight. Challenge 33. And starting today, I definitely will be counting the scores for the clickers. If you don't have your clicker registered yet, that's actually okay, because when you register, it will retroactively assign what you did now to your clicker. Okay, I have 21 respondents at this point. Any more? Euler, 22. Okay, somebody changed their mind on this one? Really? 21 and 1. Well, that's pretty good. Most people have created their account. I actually checked online and was looking at, who had and who hadn't. But yeah, it's good to see that most people are on their way. If you're having problems with that, come ask me. Make sure we can get things worked out. Now, the second question here is an important one, because I'm going to use this to then have the bookstore purchase, for you to purchase from them. So, how do you plan on purchasing your Expert TA account? There are already about 7 who've paid for it themselves. It's, quicker, easier, but for some people, because of financial aid or whatnot, they want it on their school bill. And so we can accommodate that. And last year, at least, the bookstore just sold it at the same price. They didn't even charge anything for their work, which I thought was pretty generous. Okay, that's the same number that answered the last one. Is there anybody without a clicker who is planning on buying it from the bookstore? One?
Well, I'm having mine sent.
Your what?
I'm having mine sent to me. I like it.
Oh, your clicker. But you're planning on buying from the bookstores.
I'm paying for it.
You're paying for it online. Okay. I just want to get the number. That's why I'm... The answers here were 13 and 8, which doesn't really matter except for I need to talk to the bookstore and tell them to get 8. Okay. Now back to the physics. Because, lecture's only like a little more than half over. Position conventions. I talked about designating my position, Jaren's position, with the coordinate system. Here we're starting with just one dimension. So we have the teacher up there, and as she's lecturing, like me, she walks around, and so you can measure the distance she traveled, and by convention, when we draw the motion, if the motion is to the right, we consider that positive, and to the left, we consider it negative. So in one dimension, we can actually specify our vectors using the plus or minus sign for the direction. So with one-dimensional problems, they often will say, my x vector is plus 2 meters, or my x vector is minus 3 meters. And the plus sign means to the right, the minus sign means to the left. So you actually had direction in that. So in this case, because she moved to the right from 1.5 meters to 3.5 meters, the change, the final amount minus the initial amount, yeah, you can see it up there, was 2 meters to the right, so plus 2.0 meters was her change in position. And that would be her displacement. So we have the sign convention there, how to determine if it's positive or negative and what the direction is. Going backward, I don't know why I went ahead and put the picture from the textbook for going backward as well. Here the gentleman walks to the back of the airplane, and since he was going to the left, that was a negative displacement. Now, one thing I should point out, I can't even tell that's a bold font in the images that came from the textbook. The textbook indicates a vector in bold font. That's the standard. All your textbooks do that. But of course, I can't write in bold font. So instead of using bold font, when you write it by hand, you indicate it with an arrow over it. So if I was going to write the self-same equation, those are supposed to be bolds, I would have written it as delta x with an arrow over it equals x final with an arrow over it minus x naught with an arrow over it. This is the way you write it with the hand. This is the way they write it in the textbook. So you have to be able to translate both of them and understand if it's bold, that means it's a vector. That means it has direction. If it has an arrow over it, that means it's a vector. It means it has direction. Yes?
X final and X naught, wouldn't those not be vectors? Those are just a statement.
They actually, because it's a position specified X, Y, and Z, yeah, we would still write it like that. That is a good question because a point doesn't have a direction, right? But we specify with respect to there, it's that. And so we actually are specifying a vector that goes from the origin to each. Okay. Something else that is a little subtle is in this case here where the man walked to the left, so by convention we said that was a negative displacement. The distance is still positive because the distance doesn't care what direction. And the minus sign was indicating the direction. And so the distance that he walked would still be 4 meters. But the displacement is minus 4 meters. Because the distance is just a magnitude. Whereas the displacement has magnitude and direction. Question, Reagan?
So when you're writing this, say for homework or whatever, are they going to want that sign, or could I write 4 meters to the left? Are you
in homework, you're not going to be writing either way. In homework, it's, it might have a box for to the left, or you use a minus sign for the left. But that's it. But on tests where I'm grading it, I'll want to see that you either write, minus 3 meters or 3 meters to the left. Either one I will accept because I'm an intelligent human being, not a computer. At least I like to think intelligent. We all have our hang-ups. Now, what do you do if you have more than one piece of motion? If you're adding vectors. This is an example. The full example in the book says, I think it was the teacher walks 3 kilometers to the, and it says west. Here we have the compass, and using the same conventions, east is to the right, so that's positive. West is to the left, so that's negative. And so since the teacher walked to the teacher, 3 kilometers is a long ways to walk during class. Went 3 kilometers west, we have a minus 3 kilometers here for the first trip. And then came 2 kilometers east, so plus 2 kilometers for the next part. And the question is, how do you add these together? Now, and I do have a tutorial, 40-some minute tutorial on YouTube that I made on how to add vectors. But the basis of adding vectors is just like I learned to do this when I was in grade school. How many people, when they were in grade school, first learned to add and subtract with a number line? Or at least your teacher tried to use that to teach you. Okay, a few of you. Now, that's totally the way I was taught to add. When I was a little kid going to first grade, my teacher said, okay, so you draw yourself a number line. Okay, I'm going to do a better job. You guys deserve my very best. And my very best is to not use my artistic skills at all. So you start with a number line, and then that number line you start labeling. So here's going to be my 0, 1, 2, 3, 4, minus 5. Well, nice job. 1, 2, 3, 4, plus 5. And 1, 2, that's 10. Okay, so I have my number line. I can put my minus 10, minus 5, 0, 5, 10. And so my teacher said, if I'm going to add numbers, let's say I'm going to do 7 plus 2. Instead of this new Common Core thing that everybody ridicules, we learned to do 7 plus 2 by starting at 0 and saying, okay, I'm going to go from 0. Oh man, I am going to be so sweet here for you guys. You'll have no bad arrow. I'm going to go 7 to the right, starting from 0. And then I have plus 2. Since plus is to the right, I'm just going to start at the end of the first one and make another arrow that goes out 2. Almost 2. Could have sworn that I went out to 2. Okay, that went out 2. And so if I want my answer, to get the answer, I simply go from where I started to where I ended. And so 7 plus 2 must come out to be, I'm at 9 here, and hence 7 plus 2 is equal to 9. That's how my teacher taught me in first grade. This baffles you? I'm sure it doesn't, okay? That's how we add vectors. We put vectors tip to tail. So in the problem that's shown here, I have 2 vectors. The first one went to the left, a distance of 3 kilometers. The next one started where the first one ended, went to the right a distance of 2 kilometers. And then for my final answer for how far the total motion was, the total motion started here and ended here. And so that was a distance of minus 1 kilometers. Now, we'll later learn how to do this in 2 dimensions, not just 1. And it does get more interesting in 2 dimensions than in 1. But that's how we add vectors. Now, you might say, okay, great, that's how we add. How do we subtract? How did you learn to subtract when you were in first grade? I assume everybody learned to subtract in first grade. Something that we have a problem with as physics teachers is we start thinking that people learned their math really early. So like in graduate school, my teacher would talk about, the algebra that we learned in first grade. I'm all like, really? In first grade? And I thought I was pretty advanced with math, but I assume everybody learned subtraction and addition in first grade, right? Okay, with blocks or something. That's actually very good because children don't have very strong concrete reasoning and they don't have any abstract reasoning at all. So you stick with what they have, the concrete reasoning, counting the blocks. And that's actually why our teachers did these number lines, was to give us something that was concrete but not as tangible as the blocks. Well, the way my teachers taught me to subtract was to add a negative number. So if I was supposed to do 7 minus 2, my teacher would have me change that to 7 plus parenthesis minus 2. So I'm just going to add a negative number. And that's how you do it with vectors. If I'm going to subtract a vector, I'll take the first vector, mark it down there, and then I'll just reverse the other direct vector, change its direction, and then add it just like I would add vectors. So if I want to do 7 minus 2, I would go out 7 just like I did, but then I have to do a minus 2 on that, and my answer clearly is 5. Okay, another clicker question. Select all of the statements that are correct about the use of delta x in physics. So this one you have to put in all of the answers that are correct and then hit enter. Get a few more people here. Okay, I think we must have everybody who's going to answer in. So our answers right now are, somebody just changed as I said that, 18, 1, 20 and 2. Now, if we have a very large agreement, I'm not going to go into detail unless that large agreement is incorrect. In this case, the large agreement is correct. Delta means the final minus the initial, and it also means the change in position. The change is always the final minus initial. The initial minus the final would give you minus delta x instead of delta x. And it's just not the position. X was the position. Okay, for 2 dimensions. We're not doing 2 dimensions right now, but it's being introduced just to set things up. If we do things in 2 dimensions, we tend to use x for the horizontal and y for the vertical. When I did the classroom, I did x for that direction and y for this direction, and then I would have used z for the vertical. If you use 3 dimensions, you do x and y for the 2 horizontal and z for the vertical. And up, the key here is up is considered positive, and down is considered negative by our conventions. Right was considered positive, and left is considered negative by our conventions. So just to make sure when you look at numbers and you look at problems, you understand what the conventions are for interpreting x and y. And this one here, it's trivial, but it's just saying what happens if we're adding more than one vector? Okay, more than 2 vectors, because you don't add one vector to nothing. If you're adding multiple ones, you just put them all tip to tail. So this had segment 1, segment 2, segment 3, and segment 4. And you see segment 1, at the end of segment 1, they start segment 2. At the end of segment 2, they start segment 3. At the end of segment 3, they start segment 4. And then the resultant, the total, when you add them all together, goes from the starting point to the ending point. So adding multiple vectors is just putting multiple vectors one after the other. Now, I kid you not. When I was in graduate school, I had this professor. He was really cool. He wrote a physics textbook. I've used it a few times. He put this question on the test. First question on the first physics exam. And he said, what is a plus b plus c plus d plus e plus f plus g plus h plus I? And he had a graph, and on that graph he had all these vectors marked out. It was crazy complicated. And there were a few students, I was in charge of grading. There were a few students who spent the entire test period calculating what each one of those vectors' components are, the pieces that are horizontal and the pieces that are vertical, and then keeping track of them and adding them. They spent the whole class period on that one test question. But the students who understood how to add vectors answered it in like 2 seconds and went on. Because if I add all of these together, how do I find the resultant?
From the beginning to the end.
From the beginning to end. And how far apart are the beginning and the end? They're not. So the answer was simply 0 and move on. But there were these students who didn't understand that concept. They didn't think about the question. They just said, well, I'm going to have to go through brute force, calculate this whole thing. And I mean, it's kind of harsh because you pretty much have to drop the class after you completely failed the first exam, right? I mean, if you got 1% on the first exam, it's a bad sign. And it was because the students weren't applying thought processes to answering the questions. They just tried to dive in and go through it without thinking. On our tests, we'll have about half the questions are conceptual questions, ones that you're answering based on ideas only without doing calculation. Sometimes it won't be clear that that's what the question is. Sometimes it will look like a question that has calculation, but if you think about it, there is no calculation. It's not like we're trying to trick you, but we do want to make sure students are thinking about the questions and not just trying to do it like it's a math test. Now, there's anything wrong with math. I love math. Oh man, I'm out of time and I'm like a few slides from the end. I had to put this in because it was in the textbook and I'm like seriously snail racing. Okay, remember you have the first homework assignment due tonight. You already had the reading quiz due before class. There'll be another reading quiz for Friday. There will also be a worksheet that I will put up later today that you need to do in preparation for class on Friday.